Hi, I'm Gary, and I want to show you how I use Cloudy. So we've talked about the grid command, and we talked about save line list. I want to talk about combining those to look at some cool physical insight to how nature produces spectra. To get there, let's think a little bit about excitation, de-excitation, and critical densities. So this is the O3 energy level diagram from Osterbrock and Ferland. The slides in this lecture are taken from chapter 3 of Osterbrock and Ferland. So that goes into detail. We're just kind of a flying flyby of some of the physics here to see that there's different limits for how spectra are produced. So this is the energy level diagram. It's not to scale. This is the ground term of O3, and these three levels are very close together at this on this scale. These produce the 52 and 88 micron infrared lines that can be very strong. The excitation from this ground term to this 1D term here produces the 5007, 49, 59, 03 rate lines in the optical. So for some conditions, for H2 regions, planetary nebulae, these can be the strongest lines in the optical spectrum. They're very, very important. And so there's a simple low density limit we can think about. So we have an O double plus sitting in an ionized gas, and it's surrounded by free electrons that have a certain kinetic energy. So for most nebulae, it's 10,000 degrees. So the average kinetic energy is about 1 electron volt, is how it works out. And these free electrons can hit O double plus and cause an internal excitation. A electron in this triplet P ground term can rob the kinetic energy of the colliding electron and take away its kinetic energy and use that energy to promote an electron to this level. And that level in the low density limit, the odds are it will emit a photon and go back to the ground state. So that's called collisional excitation. And so in low densities, every collisional excitation leads to an emission of a photon. That's called cooling because it robs the thermal energy of the gas. So the thermal energy, NKT kind of a thing, in the gas, if the thermal electrons, the free electrons, hit the O3, they lose kinetic energy and produce a photon. So it cools the gas because heat is turned into light. There's some atomic data that enters in this. That's why the cloudy download is as big as it is. We need to be able to figure out excitation and de-excitation rate coefficients. The rate coefficient in Osterbrock and across cloudy is given notation Q. It has strange units, cubic centimeters per second. So it's hard to visualize what this is unless you multiply it by the electron density for the case of electron collisions. And so the collisional rate is going to be the rate coefficient times the electron density. This capital C is Q times N. And this has units of a rate, seconds to the -1. And you want to compare that with the transition rate, the Einstein A for spontaneous decay producing a photon. So that's the capital A. It also has rate units, so it's per second. And there's a critical density which is the density that tells whether if you put an electron in an excited state, will it make a photon or will another electron come in, collide with that excited state, rob the energy and give the energy back to the heat content of the gas. That's called collisional de-excitation. So the way you approach this is write uh, a balance equation. Again, these are snippets from the Osterbach book. And so the term on the left is electron density. For the case of O3, this would be the O double plus density. And then Q is this rate coefficient, uh, which comes from the quantum mechanics. It's a very complex quantum mechanical problem. So that's the excitation rate per cubic centimeter per second. You should always track the units. Units are your friend. And that's going to balance decays from n equals 2. And so decays can be, this is collisional de-excitation, Q from 2 to 1. So that would be the density of the n equals 2, the excited state times the electron density, because the electron density times Q becomes a rate. And then this is the spontaneous Einstein A, the emission rate. So at very, very low densities, uh, this is a linear term This is squared, this is squared. And on the right-hand side, if you go to low densities, this term gets small faster than this term. So very low densities, if you take the density down to zero, this is the only term that matters. So every excitation makes a photon. The solution to this equation is given here, and it tells you the population ratio. So it's basically the excitation rate per second divided by the spontaneous emission rate times this correction factor, with a lot of terms that depend on the so-called critical density. The critical density is defined as the ratio of the Einstein A divided by the rate coefficient. It would have units of densities, cubic centimeters. And so for densities smaller than the critical density, the emission goes as density squared, the emission per unit volume. And for densities bigger than the critical density, the levels in LTE and the density goes up linearly with density. So there's two limits for the equation. We'll see cloudy go to these two limits in the next video. So there's two limits, one set by the critical density, and critical density is the density where there's a 50-50 chance of a collisional de-excitation or spontaneous emission of a photon. In low densities, we can neglect collisional de-excitation, so every excitation makes a photon, and the emission in a line per unit volume depends on density squared. So you go through the equations, you end up with this kind of a rate. At very high densities, the levels have come into LTE, so the population is simple again. And in that case, the emission per unit volume is proportional to the density itself. And so you can follow through the equations. You have a Boltzmann factor here. The density of the O3, a Boltzmann factor, and the A is the emission coefficient. So the critical density is important. It's so important that we report it. We've seen saved line data before when we looked at the docs line list input script. This is one of the save files that it produces. So this reports the atomic parameters for all the lines in the code. And what I've done is it's a big report, and I've cherry picked out the 403 lines we've been thinking about. So it's gives it by the label of the species for the spectrum says O3. The tricky bit, there's two spaces between the O and a 3 because we have four characters here. Next is the wavelength. The code does parse the angstroms or the microns. The code works across the full spectrum, so the units change as you go across. So this is going bottom up. This is a famous infrared line from that ground term, 88 microns. Here's the line 5007, which is frequently the strongest line in the optical spectrum. This is a much weaker line, but you can combine this with 5007 to get a temperature. And then finally, this is an O3 line in the vacuum ultraviolet, the FUV. There's a lot of numbers that are entered here, but the first interesting thing is the Einstein A, the seconds minus one. So you can see there's a spectacular range of A's. So the first line, the 8084 line, is what's called a permitted line. So in quantum mechanics, this is electric dipole allowed transition. So it's kind of like Lyman alpha of hydrogen. So it's really fast. These remaining three lines are forbidden lines. Interesting word. We're looking at them, but they're forbidden somehow. This is language carried over from the 19th century when all this spectroscopy started, 19th century through about 1930. And in the notation, you'll see in the older literature, first they'll use Roman numerals for the O3, and this first line, the electric dipole allowed line, would be just O3, and then depending on which order of the transition you have, there can be one or two brackets around these. So the A has gotten down quite a bit. So this is electric dipole. The remainder are either electric quadrupole, magnetic dipole. There's a range of possibilities, but you see that the A is very slow. So for 5007, if you excite a level, it'll hang around up there for 50 seconds before it makes a 5007 line, even longer for the 88 micron line. This is the collision strength, something we haven't talked about. It's described in Osterbach. This is what you use to get the rate coefficient, the collisional rate coefficient. Both oscillator strengths and collision strengths were an attempt to patch up classical scattering theory to get the quantum mechanical answer. So they are a correction coefficient of order one that makes it so that the classical equation for scattering or for emission, Maxwell's equations, that stuff, it fixes it so you get the quantum mechanical answer. So it's a number frequently of order one. So that means the classical answer isn't terribly bad, but this makes it much, much better. Second to last column gives critical density, and you can see there's a huge range of critical densities. It's driven not by the change in the collision rates, because these collision strengths are all about the same. It's driven by the spectacular range of Einstein A's. You can see there's 13 orders of magnitude range in A. And so there's a 13 orders of magnitude range in critical density. And so we'll see this when we do the ranging calculation in the next video. The last column is damping coefficient. We don't need that here. It takes into account the natural broadening of a line due to the finite lifetime of the excited level. Because the excited level is short-lived, nanoseconds for the U1 transition, is broadened by the Heisenberg uncertainty principle. And this damping coefficient, you feed through a Voigt function, the mathematical description of this, to take into account the natural broadening. So with that, we'll set this aside, generate a line list file for the next video, and then set up a sim that's going to vary a density over 20 orders of magnitude and see how these lines change. I'll see you then.